So I'll just begin. I'm not really sure how this is going to go, but maybe that'll be the theme of this lecture. It's going to be pretty casual. I'm not one of your usual lecturers. My name is John Wu. I'm an associate astronomer at Space Telescope Science Institute in Baltimore. I'm also the applied AI scientist there, and I talk a lot about large language models. I'm always happy to talk more about that. I also do a lot of my research in machine learning, specifically in deep learning. I should also mention I have visiting appointments at Johns Hopkins in the physics department as well as in the computer science department. But today I want to give you a taste of how machine learning has the ability to transform astronomy, really to leverage all the data that are available, in the sky that we can record with various instruments and try to make the most of it. Okay, so the example that I'm going to give is how to train, basically how to think about and how to train convolutional neural networks. It's a popular form of deep learning, and it is useful for processing images at the pixel scale. So as I get started, I'd like to motivate with a little example. I have a slide that is not advancing. So let's try this again. Where is the slide? Here it is. OK, good. So I have a daughter named Bethel. She's almost 6 years old. This is us at a Baltimore Orioles baseball game earlier a couple of weeks ago. Hopefully I'm going to see a baseball game in Tianmu as well soon, next week. But anyway, one of the American pastimes is learning, teaching your kid how to throw a baseball. I don't know why this is showing up here, because this is not what I see on my screen. Anyway, so one of the questions I like to think about is, as we talk about how to learn to do something like train a neural network or think about machine learning as a whole, I'd like to consider stepping back and just being like, what does it mean to learn to do something that's new? Something like teaching a 5-year-old how to throw a baseball. This is an American pastime. As a dad, I'm obligated to teach my daughter how to play catch. How do I teach her to throw a baseball? And I know what you guys are thinking, because you are all astronomers or physicists or aspiring ones, and that means that we must be very quantitative. We need to send our kids to cram school so that she can learn her multiplication tables. That way she can get a leg up on algebra, of course, and only when you know algebra, then you can solve the equations of motion and learn something about projectile motion in your Physics 1 course. And then as you get to Physics 2, we all know the most elegant way to think about the classical dynamics, of course, is through the Euler-Lagrange equations. And maybe once she's mastered this, perhaps the canonical forms in the Hamilton's equations, at that point, maybe we can start to learn how to throw the ball, right? Is that how we learn how to teach her to throw a ball? Alternatively, we could just go and try to throw the ball, see what happens. As you can see, if you have very good eyesight, you can see that guy is a Yankees fan, so he deserves it. Baltimore's Orioles and Yankees are not friends with each other. These are two different styles of teaching philosophy. I don't think any of them are particularly right or wrong, but I do like to emphasize that there are different styles that we can think about how to learn. And specifically, this top-down style of just saying, let's just throw the ball and see what happens, is kind of the way I want to progress today. We're going to try to just implement a neural network with some code. I hope you feel empowered by being able to just execute some cells. You don't have to do this now. I will share the notebook later, so don't feel like you have to follow along in real time on your computer. But I think you can learn by trying things out and seeing what works, what doesn't work. This helps you build some intuition in a way that maybe just knowing how to solve the equations of motion does not, right? Teach you how to throw a baseball. And hopefully that also gets you a way to understand the big picture and understand things like the training dynamics and what are in general the types of problems in which these types of neural networks do succeed or don't succeed. I want you to build that kind of an intuition. There's, of course, also bottom-up approaches. You can build on a mathematical foundation, and this is very useful. This is essential in many quantitative fields, ranging from math to physics and astronomy. And I think having a precision and a good understanding, a definition, and knowing how to prove things is also essential, right? But sometimes as you begin with the top-down approach, you feel more motivated to know that, yes, I can actually train a neural network. I can even use this in research. And then you can really fill in the gaps of your knowledge and pursue that, knowing that this is actually fruitful for you. And then you can say, OK, let me go and make sure I understand all of the matrix algebra and all of the complexities that come along with hyperoptimization. But we can understand those details later. So I hope that you get a sense of what style works better for you, but we're going to try the top-down approach today. So with that, I'm going to launch into just a few slides about CNNs. If you happen to attend the colloquium yesterday, you might have seen some of these slides, but I think it's good just to give, again, some of the big picture. So with neural networks, the artificial neural networks were loosely inspired by biological neural networks. So if you open a biology textbook, you might see an image like this on the left or the right. So on the left, this is a cell, a neuron, which is a type of cell in your brain. And it has these things on the left side called dendrites. They're kind of like these little spiderwebby looking things where signals can actually enter the cell. They can somehow, these electrical signals get processed within the cell, and then depending on how the processing goes, it might fire off a signal along the axon to the right. And that axon has these terminals which then connect to other cells in the brain. And it turns out that cells in the brain, these neurons, are organized by what they do. So if you look at within the brain, again, this is not my area of expertise, but my understanding is that there are regions of the brain which are organized in a way such that they can accomplish tasks when used in tandem. So this organization scheme is helpful. Both of these are actually helpful paradigms when we think about artificial neural networks. So you might have some signals. We're just going to arbitrarily represent them as x's, and maybe it's a vector of x's, x0, x1, x2, and they can enter through your artificial neuron. Now, this artificial neuron is actually just a very simple operation. It's a mathematical operation, perhaps a matrix multiplication plus some sort of bias term. And that is what's happening. We're pretending that's what's happening inside the cell body. And we can then decide whether or not we want to activate the neuron, right? So perhaps the signal is not above a threshold and it doesn't send out any signal, it sends out a 0. But if it's above a particular signal, maybe it's positive or something, then we go and say it can propagate that signal. And not only can we have a single neuron, but we can have multiple neurons that are sort of organized in an input layer that receives some sort of input. We're going to see this in the case of like an image, a set of pixels aligned in a grid. They can be then passed on to maybe a second layer of neurons, which work in tandem to process that first layer's inputs and so on, until you progress through the neural network, and then you arrive at the output layer. And so I really want to focus on the idea of convolutional layers because they are the building blocks of convolutional neural networks, and this is key for for processing image data. So whenever you think convolutional neural networks, or there's other more modern sort of variants of these, things like vision transformers and things that you might hear, but really what you should be thinking is, I have a 2D grid of pixels. This is a very particular way of representing data, right? It's a natural way of representing things like images. And so if you have images that are represented that way, then the way you want to describe or process your data should also be aligned in a similar way. There's a piece of jargon called inductive bias. And oftentimes what I think of with inductive bias is, does the way I try to solve the problem align with the way that the data are represented to begin with? And so the inductive bias of a convolutional neural network is really just quite similar to matched filtering. If you're an astronomer and you're familiar with matched filtering techniques, this is essentially what you're doing, sequential matched filtering over a range of scales. So our blue matrix here is just a 5x5 grid, and this is your input image. You can think of like each pixel as being x0, x1, x2, and you can index through all these pixels. You also have a whole bunch of morphological features, but one of them I'm showing here. And that's just another matrix. In this case, it's a 3x3 matrix. This is a toy variant of it. And you can index the pixel values within it too. You should think of it as a little tiny image. And that little tiny image can contain a morphological feature. Maybe it has something like a gradient, or like an edge, or something like a little mini PSF, a point spread function. Whatever it is, it contains some shape information. And as you take that white 3x3 matrix, the morphological feature, you can then go and slide it over the underlying input and see where they overlap and determine if they are similar, right? If they are very, very similar, then basically if the inner product of the blue region underneath the white region is very high, then hopefully you will end up with a high activation, and you end up with a strong activation, basically meaning that this is just very similar at that position. But of course, you can also slide this morphological feature, or this representation of it, over your underlying image. And this now tells you, how similar at each position is my morphological feature to the input image. And so that green resulting set of features now really is just a map. It's a map that says, oh, it's this similar at these different locations. And you'll notice that if you have good eyesight that I put my little f back over there because we actually then passed it through a nonlinear operator. This is necessary for linear algebra reasons. You don't want a whole bunch of linear operations in a row because they can just be represented by a single linear operation. But if you have these non-linearities in between, then you can learn arbitrarily complex functions. Don't worry about that if you don't really want to think about linear algebra. But the cool thing here now is that you can take your map of your features, and in fact, that is just another image in some sense, right? It's a more high-level abstraction of what an image is, but you can then try to learn morphological features, basically look for the presence of interesting shapes within this map of features, and then scan over that again and process that as the next layer of inputs. So what this allows you to do is sequentially look for morphological features over a range of different scales. And so maybe you've got some input image here, and then you're able to find things like point sources, or you're able to find gradients or edges. And then you can start to find other objects like curves or more complex shapes that are built of a nonlinear combination of those more simple features. And then perhaps you find dust lanes and H2 regions and the bulge and so on. And then finally you can get these really high-level representations of the neural network. Because again, you're just building on what you've already found. And then at the end, you've kind of got this big list of descriptions of your galaxy. We're assuming that this is being trained, right? And so if this now is taking the galaxy image and decomposing it into a whole bunch of features, you can almost think of this as like turning this into a big table where the columns each list some sort of morphological meaning. One of them might say, how point source-like is this galaxy? One of them says, is this asymmetric? Or how tight-winding are its spiral arms? Does it have tidal tails? Blah, blah, blah. All sorts of things. But the crux of this is that it needs to find some sort of features that are able to allow it to succeed at a downstream prediction. And so this is the realm of supervised machine learning. We are supervising it. We are making it, our convolutional neural network, or CNN, is going to give us a prediction. And we want to be able to compare that. Let's say the prediction is something called the gas phase metallicity. If you don't know what a gas phase metallicity is, you should just think of that as the chemical abundance of relatively heavy elements, things like oxygen, integrated, this is an approximation, but integrated over the entire galaxy, over all that galaxy, or average there, relative to the amount of primordial hydrogen that it contains as well. And this tells us something like a clock of its star formation history, and it's a summary statistic of its evolution as a whole. So that's what I mean by Z gas here. So there's some sort of gas phase metallicity. It's got this number, 8.6, let's say. And then we can then compare our prediction against the true value. This true value is something that we need to obtain a different way. So for instance, with spectroscopy. And then we can say, is our true value close to the predicted value here? If it's not, then that means we need to tweak our neural network a little bit. And we can evaluate this by defining a loss function. This is a choice that we make. So we can say the mean squared error is how wrong we are, right? Or the root mean squared error. Or you can define any loss function. You might want to say, I don't want to penalize outliers, so I'm going to choose something like an L1 loss function, right? The absolute value of the difference of these two. So you have a choice to make, but you can say, let's quantify the error. And not only can we quantify the error, and this is the part where I don't want to get too into the details, but we can in fact compute the partial derivatives of that loss with respect to every single neural network parameter that exists in there. So all of the W0, W1s in every single layer, there can be 10 million of them, but we want to say what is the derivative of that part of this with respect to every single parameter that exists in here. The good news is you don't have to do any of the calculus yourself. There are numerical methods. There are, if you use Python or PyTorch or JAX or any one of these things, packages or pieces of software that have automatic differentiation, they handle those operations under the hood, and you do not have to worry about them. But if you want to know more about it, it's really just saying what is the contribution of every single parameter that gives rise to this loss. And then when you take the gradient of it, it makes an approximation of how do you reduce that loss function, what is the direction you need to change the neural network parameters, and then you can then update your parameters accordingly, and then continue this in a big loop where you make a new prediction after you've adjusted the parameters and look at the true value and see if you're closer. You want to do this over very, very large data sets. You want to do this for a diversity of data that is representative of when you're actually going to use it in practice. So this is like the super quick intro, the 15-minute version of how to train a neural network or convolutional neural network. Maybe I'll stop really quick and ask if anybody has any questions so far. crystal clear. That would be surprising. Okay. Now, so if that made absolutely no sense to you, don't worry, because we're going to go and do this in practice now. So what we can do here is basically train a neural network. I can do this. This is on a platform called Google Colab. You're welcome to grab this. I know it's probably going to be hard to execute on your phone. So again, I will share the link to this, and you can run it hopefully on either a laptop or whatever. Maybe you can even run it on your phone, which would be very impressive. But don't worry about trying to follow along if you don't want to right now. Okay. So, introduction to convolutional neural networks. So I've already basically said this, but we are now going to define this task. Given galaxy images from the Sloan Digital Skies survey, can we predict the gas phase metallicity of that? So that's typically something you need spectroscopy for, right? So it takes a lot more time. You have to take a dedicated spectrograph and then plop a fiber down and basically collect the light and divide it up as a function of wavelength. Then go and model all those things according to some simple stellar population assumptions and a whole bunch of other assumptions. And then you model those parameters and you derive a ground truth. And you say that is maybe my gas phase metallicity that's spectroscopically constrained. What we're going to do here is we're going to just try to use some images, and this is indeed actually something I did towards the tail end of my PhD thesis, and it convinced me that machine learning actually was something real, and actually made me pivot from doing more observationally focused work in galaxy evolution, which I still love, but to focusing more on machine learning. So our roadmap here is that I'm just going to briefly show you how to load the data set. And then basically we're just going to go and build the convolutional neural network from scratch. And we're going to go and optimize this model using the kind of what I just mentioned before. How do you progressively update all the weights in a little convolutional neural network and evaluate how well it performs. At the way bottom, there's like a little bonus objective in which you can use a pre-trained neural network, a neural network that's already been trained on images of cats and dogs and cars and just random stuff that people have collected images of, and it's able to label those things. And we can slightly tune it, we can fine tune it using a lot less compute to achieve this galaxy metallicity prediction. And I'll talk a little bit about the reasons why that's even possible. Okay, so again, as we said, we're going to try a top-down approach. You can, just click run all. Actually, in fact, if you're going to run this, I recommend you go and click on this top bar on the top right side. You're going to want to make sure that there's something called change runtime type. And if you want this to be running quickly, you want to select something which has a GPU option. So GPU stands for graphics processing unit, and you can essentially run many matrix multiplications in parallel. This is a pretty old GPU. It's about 9 years old, so it's nothing like super fancy. It's very low power T4 GPU, but it's still quite a bit faster than running it on a CPU. Okay. So I'm actually not going to execute this now, but I've already run it before. And so if you hit run all, you will just be able to let all the code run. It should hopefully work. And in fact, what will happen is you will have an optimized convolutional neural network, and I'm going to just scroll to the bottom here, that can go and predict galaxy metallicity to about 0.9 dex or so, which is extremely, this is extremely impressive. This is not something intuitively that I thought was possible. And so this is the true metallicity shown on the x-axis. This is the ground truths. And then these are our CNN predictions, where we have actually, in this case, trained a very tiny neural network, only about 20,000, or no, not even, 100,000 parameters, but still small by sort of modern neural network scales, and is able to basically learn from a small data set. So let's go back to the top here. I'm not going to scroll it. So there are some cells that explain how to set up the neural network. Don't worry too much about what's going on in there, but this is basically like importing the right libraries and things. There's nothing particularly interesting in there. But it is interesting to think hard about the data that we're using. So we're going to use a data set of 14,000 galaxies. And these are galaxies that exist in both STScI spectroscopy and also have been imaged, which is essentially a superset of those that have spectroscopy. And so the inputs are going to be in JPEG format. I just did that so that it's easy to transfer the data. They're essentially compressed, and so they're not optimal, but they're very, very small. And that takes 3 optical broadband filters, G, R, and I filters, and that maps to the blue, green, and the red channels. Okay, so 3-band imaging, and I think they're like something like 140 or something, 160 by 160 pixels across. So 3 by 160 by 160 is the size of the input. I mean, if you can do that math in your head, that's of order 750,000 inputs, right? So that's actually a lot of inputs, but we're going to be able to process that with our neural network. And then the targets is just a single quantity. This is the gas phase metallicity, and it's often called either Z gas is what I call it here, but 12 plus log O over H. And I've already selected a clean subsample. So normally you would want to do some more data cleaning. You should definitely always look at your data, visualize it, and understand the weird selection biases that are at work here. In this case, this is basically a random subset of objects that have signal to noise greater than 3 in some prominent optical emission lines, which is a pretty standard cut. And they're selected by the STScI main galaxy survey, so R magnitude, broadband magnitude of 17.78 or lower. Okay, so if you run this next bit, this is just going to download the galaxy. And importantly, so we get 14,000 galaxy images. It will unpack them in the nearest directory. And then we can go and load them into something called pandas data frames. So pandas is just a convenient package which is able to manipulate tables pretty readily in Python. So pandas, or PD right here, I'm going to open a CSV file. CSV stands for comma separated value. It's just a simple format of storing data. And in fact, our galaxies, which we've just downloaded here, we now know that we are able to load the 14,000 galaxies. And if you look at the head, the top 3 rows of this table, we can nicely visualize that here. So that's what this is showing. And just very quickly, there are the top 3 rows. There is a unique object identifier, so each galaxy gets its own object ID. RA and DEC, hopefully you know, is the position, the coordinates of the galaxy in extragalactic sky. Z, in this case, Z or Z, is the spectroscopically confirmed redshift. And then, maybe you're not so sure what these three things mean. And so the thing that you should do is go to the SDSS MPAJHU catalogs, which define the data model and tell you exactly how these things are derived. But I'll just tell you right now, LGM tote P50, this is basically the logarithmic stellar mass. It's the median estimate for that based on some spectral energy distribution fitting. The SFR is tote P50 is the median value estimate for the star formation rate in units of log units of solar masses per year. And then OH P50, that's 12 plus log O over H, the metallicity, exactly what we want, and that's just in dimensionless units. Okay, you can see approximately the range of values that they take. And then, as I said, we also want to think about how to load in our images. So we've got these 3-band images. It's 160 by 160, and we're going to want to be able to load them up. So I've got a little bit of code here. Oh man, these are really overlapping. I've got some code here, but now I kind of want to change this. So let's go and make this so that they don't overlap so much. And I'm going to run all. Hopefully this doesn't break everything, but we have basically, I'll just show you the pictures here. We got just a couple of randomly selected galaxy images in our data set. These images are generally, okay, well, there goes that. These images are galaxies that are representative. We just selected 6 at random. We're visualizing them. So again, they're loaded as JPEG. I think my notebook is now re-downloading everything because I'm doing this on the cloud, on the Jupyter or on the Google Colab platform. But once it's done downloading, it's going to show them again. Hopefully it's even going to show the same ones again because I gave it a random seed, and I hope that means that it will set the randomness to be repeatable, reproducible. And I think these are indeed the same ones that we just saw. But I have to zoom out. And what we also show is Z, I should really have written Z gas, is the gas phase metallicity, the ground truth metallicity that we're assigning. So again, what we want to do is say, given an image like this, can we possibly recover the gas phase metallicity? And can we do this in a generalizable way that not only do we do it for a bunch of images that we've seen before, but we also want to be able to succeed for other SDSS galaxies that we haven't seen or trained on. Okay. So I talked a little bit about inductive bias before this. And let me just talk now a bit about okay, so we already know that we can solve this problem, and we're about to go do it. But it's helpful to think about how do we design a neural network in a way so that it can actually tackle this problem. I think I motivated this a bit by saying that convolutions are the natural solution to things that live on a grid, right? To images, which kind of are confined to a grid. You don't have pixel sizes that vary, like, you know, across the grid. They have this constant sort of set scale. There's other types of assumptions that we are always making. Like, we might think that the universe is isotropic. There's no preferred direction. And so that means that we don't really think that galaxies ought to be seen at any particular position angle, right? So the rotation of the galaxy sort of within the plane of the sky is arbitrary. In fact, it doesn't change any of the physics, and it shouldn't change the galaxy's metallicity. So that's something useful to think about. So the galaxy metallicity might be invariant to rotations. Hopefully it's also invariant to reflections. You might think that the handedness, if you have a galaxy spiral arm, right, maybe that spiral arm is going one way or maybe it's going the other way, the parity or the chirality of galaxies. Hopefully it should also be invariant to that too. And so if so, then we can actually think about how these symmetries enable us to augment our data set. We can actually effectively make our data set larger because we can take our input images and we can rotate them. We can flip them, mirror image them, and we will get almost like new-ish data examples. We are effectively making our data set a bit larger, but it's correlated to the existing data set that we have. This is actually a nice little trick called data augmentation by leveraging, you know, the physical or geometrical symmetries that we know are present in the problem. And I'm just going to say, you know, we could make arbitrary rotations, but in our case, we don't really want to. If you think about the fact that we have a square image, you know, going 90 degrees is reasonable. If you go somewhere in between, then you have to design some sort of interpolation scheme because your pixels are now sort of oriented at a different angle. So then that starts to change exactly what's going on. So we're just going to make rotations that sort of are at 90 degrees, you know, 180 or 270 degrees or no rotation. We might do reflections. We can do that across the vertical axis. We could do that, or the horizontal axis, the vertical axis, or even across a diagonal axis. There's a question about, do we want to do any translations, right? Can we take our image of our galaxy and kind of move it away from the center? The answer is generally actually yes. Convolutional layers, convolutions are translation invariant or actually translation equivariant. But I'm not going to get into that. We're not going to go and do any sort of like moving, you know, translating the image around, basically scooting it to the left or right or up or down. Okay, so let's not do that. So at this point, we now have decided we can augment our data set by generating these new examples according to the symmetries. And in fact, the symmetry group, based on rotations of 90 degrees, 180, and 270, and doing the reflections that we just said, is something known as the dihedral 8 group, or the D8 group action. So under this group action, so under any sort of transformation that we choose arbitrarily, we should not change the galaxy metallicity. So we are effectively improving our data set size. Okay, we are now able to go and open this data set and load it into memory. I think I'm going to skip over the messy details of this part here, except to say it's each of these steps is essentially just, you know, saying we're going to go through, you know, all of the labels or all the names of the galaxies in our table, and which should have a corresponding image in JPEG format in a file, or as a file in a folder like that we've already downloaded. So this is the way that I've set it up for you, and this should just work. And what you do is you can go and use some nice Python image libraries to go and open the image. You convert it into a NumPy array, and then kind of, this is a bit funny, but you can then turn that into what's called a PyTorch tensor. Okay, and so when you hear PyTorch tensor, again, you shouldn't really think of too much more except that it is essentially an array. It is a multi-dimensional array of numbers. Those numbers capture the pixel values. Again, so we're still thinking about, you should still be thinking of these guys here. Each of these have pixels. In fact, there's 3 channels, the red, green, and blue, which sets the color here. And their relative intensities tells you, oh, this is why the bulge is redder or more yellow. It's because it has more higher intensity in the reddest channel, in this case the I band, than in the G band channel, which is the bluest one. Okay, and so you've got, you know, these sort of 3 by 160 by 160 images, and you're now basically just doing, you know, making sure that they're in the right format. So don't worry too much about this, but what we end up doing is going and putting that into a giant array, which can be loaded into memory. And this will make this a lot faster to actually operate on. And then we need to go and design this data augmentation thing that I just mentioned, the D8 group. This is actually quite simple. So we can make a function which accepts an image. And then we basically say, OK, let's go and just by random chance, we might want to do some sort of flip or rotation. And so based on essentially a random integer that we choose out of, out of this routine, we can then either rotate it by 90 degrees or more. And then we can also do things like flip the image along a particular dimension. So this gives you all of the possible ways that it does this D8 group. And so it takes in an image and it returns the transformed image. Again, if you're not exactly sure what this does, I would recommend you can just go and put the image in and try running this function a whole bunch of times and watch it randomly rotate or flip the image. The other thing we're going to do is now divide our data set. We're going to define our data set using this thing called a galaxy dataset object. This is getting into the nuances of how PyTorch works. And so PyTorch, again, is one of the most commonly used machine learning packages. So if you're interested in using it, it's helpful to eventually figure out how this works. But for now, I'll just say all you really need to do is come up with a way to define the initialization. So when you create a galaxy data set, this is like a custom class I'm creating here. But all it does is tell you essentially which index, sort of at which row number are we looking at, and what kind of augmentation scheme might we be doing at each point, or overall. And then so we've got all of our row numbers, and then we can, based on a particular index, we might be able to go and select an image. We might also be able to then select the same exact corresponding galaxy metallicity, and then we might be able to apply this random transformation, right? So this is if self.augment, if this exists, if this is possible to do, then go and return the randomly transformed image. That's what this next line does in Python. And then then we can go and return the image and the target. Now, if you're careful, you'll notice that there's some other lines in here. So we actually normalize the images. So we subtract off the mean of the image in each of the 3 channels. We also divide by the standard deviation. This is very common to do in machine learning. The other thing we're going to do here is also now make a division of 80% of our data set. Oops, I'm sorry. We're going to take 80% of our data set and we're going to save that as our training data. These are the data that we're going to go and try to learn from. And then we're also going to define 20% of our data set, which we will never train on. But what we want to do is take a look at how we perform on these held out validation set examples and see whether or not we are learning in lockstep. Not just on the training set, but also we're generalizing to the validation set that we are not training on. So that's what's happening in this cell. And you also notice that so in this case, I'm using the nomenclature y kind of as like the output. Y is the prediction here, or it's the training target. And so I'm taking the training target, again, the gas phase metallicities, and I'm saying that for everything in the validation, or from the training set only, we're going to go and compute the mean and the standard deviation. That way we can standardize that as well. It just makes it easier to make predictions. Okay, so the average metallicity in the training set is something like 8.9 in units of 12 plus log O over H. And the standard deviation is something like 0.18 in the same units in dex. All right, and we can now go and do a couple of things. So so we've defined something called a data loader. The data set is basically the class that we just talked about. This tells you how you might go and select a galaxy out of there. A data loader tells you how do you grab a whole bunch of these randomly shuffled, because we're going to want to train on random instances of these data sets, and grab a whole bunch of them all at a time. And so this data training loader is we can make it iterable. That means we can go iterate through it. We can grab the next one, basically the first one, and we can get a batch that is basically a set of images, xb, so that's the batch of images and inputs. Yb is the other thing that we grab out of that, and that's the batch of targets. This is the gas phase metallicities, and that's all in the units of 12 plus log over H. Yes, question?
Maybe it's more of the details, but when you're doing this loading of a bunch of galaxy, and you're doing this interactively, are you selecting different galaxy each time? Can you repeatedly select the same galaxy?
Yeah, great question. So are we selecting the same galaxy or different ones? So we are defining so with the data set, this will tell you how to grab a specific galaxy instance. And then when we make the training loader, this tells you how do you randomly load galaxies for training. And so, so I should have said this earlier, but this last line, we make a training and a validation loader. So for the training loader, we have our training data set. We say we want to grab 64 of them at a time, because we can actually operate on a whole bunch of these in parallel, so that we can basically learn from all of them at once. And we're going to shuffle them. That means we're going to randomly sample them, okay, without replacement. So we're going to try to iterate through your entire data set, your entire training data set, through the train loader. You're going to grab 64 at a time, in chunks of 64 galaxies at a time, until you've hit all of the training galaxies. And you can see down here, there's 11,212 training galaxies. Okay, now if you were talking about the validation data set, we don't really need to shuffle these, because in fact it's helpful to preserve the order of the validation data set so you can later cross-match to their other properties perhaps. We can make a larger batch size, because this is just seeing how well we perform. We're not trying to optimize the neural network, so we're actually going to grab more at a time. How many you grab makes almost no difference. It does make no difference in terms of the CNN. Your CNN is going to operate on each of them in the same exact way. But what it can do if you have too large of a batch size is it can make your computer out of memory, and that would be bad, because then you basically have to restart everything. But with the validation data set, you are not trying to train anything, so therefore you can afford usually a larger batch size. That's why I have a larger number there. Thanks for that question. So there's 2,803 galaxies in the validation set. And so if you think hard, 11,212. If you divide that out by the batch size by 64, it should be something like 176. So each time there are 176 iterations, training steps, as you are trying to train. And so doing a full pass through your training set is called an epoch. So there's a bit of jargon here, but hopefully this all these things are self-consistent. I don't want to go through all of the terminology right now, though. Yep.
Just again, one might be a detail again, but I was wondering about does it have to be an exact multiple of the batch size? For example, if you divide.
Yeah, so no, the answer is no. You don't. It doesn't need to be the exact multiple. Your batch size can be, just one object and then a whole bunch of zeros. It doesn't really matter, or you can just drop that if it's going to be a random small sample. In practice, it doesn't matter a ton, but you can zero pad, basically just fill it with a bunch of dummy zeros, and as long as you're bookkeeping your way through, then you just ignore those zeros later on. I mean, you have no training targets for them anyway. So it's not a problem in practice, but it is good to be careful about that. Any other questions? All right, again, I know that there are a lot of details in here, and I'm starting to maybe get bogged down a little bit too much in them, but what I do want to talk about is the architecture of the neural network. So this is actually another way of sort of visualizing what I had shown earlier in the slides. What I really want to show, if I can find it, is this spreadsheet demonstration. So there is a Google spreadsheet here, which basically shows a one-dimensional 28 by 28 grid matrix. This is a handwritten digit from a data set called MNIST. There's handwritten digits from 0 through 9 in Roman numerals, or not Roman numerals, in Arabic, I guess, numerals. And so then you've got, this is a 7 here, and so somebody has drawn that, and it's got this kind of bar going through it. I think this is a 7. Hope it's not a 3. In any event, you can see that if you look carefully, I'm going to go and sort of zoom in more now. There are pixel intensities that range between 0 and about 1. So you can see their pixel values here. This one's actually 0.996, but if you look at this, it sort of rounds up to 1. But the intensity is sort of representative of this monochromatic image. Now, what I really want to impart is, I mentioned that there are these different filters, right? And so one of these filters is this particular shape. And it's helpful to think, actually, let me go and change this shape, in fact. Let's go and do something like this. 1, 1, 1, minus 1. This is a live spreadsheet, as you can see. So we've got a shape this is a filter, right? But remember all of your convolutional filters, and we're going to perform the convolution over this input on the left here, and we're going to go and see what the resulting output is on the right. But what we really want to focus on is this convolutional kernel. If you have a row of ones on the top, and then a bunch of zeros, and then a bunch of minus ones at the bottom, you know, that is a particular shape. It's actually a gradient, right? You've got high intensities at the top and so low that you've actually got negative intensities on the bottom. And so you can think about what does this, where would this sort of most match your handwritten digit over here on the left? It's helpful to think a little bit about this. And you can almost do it by eye, right? You can see here's a place where you've got some ones up here, and then you've got, you know, sort of lower values down here, and you've got the lowest values here. So maybe somewhere like this is where we expect, you know, it to operate the high, basically give us the strongest match. And so if you click right here, indeed you find that this is the convolutional output, right? So what I've done is I've taken that filter, I've convolved it over this image, and I'm looking at the map where the activations land. And this is one of the higher values here. And indeed, this is exactly where it was centered over this grid of pixels that I was just talking about right there. And it's because the underlying image, if you remember the slides that I was going through before, the underlying image at that position is quite similar to the filter here that we've designed. Like I literally just made this by hand, right? And what this finds is the bottom edge of something, right? Yeah, this is the bottom edge of a handwritten digit of 7. You're finding the bottom edge right down here. And in fact, it activates strongly all over the bottom edges, which correspond to the bottom of this sort of top bar of the number 7. You can do something similar too, where maybe you design something that looks like this. And analogously, this, sorry that you can no longer see the Roman numeral 7 up there. But again, what you're finding now is the places where, for example, this gives a strong value, a very high value. This is activating on, this would be the right edge, right, of the image. And so this is now activating here because this is similar to that convolutional filter that we just designed. You'll notice that if you look at the other side, this should actually give a very, like in this region, it should give a highly negative number. And indeed, I think if you were to look in this area, this would actually be quite a negative number. But we are, as I said, we've imposed this nonlinear function where if it's below a threshold of 0, then it just cuts off and returns a 0, which is what's going on here. So if you want to build up some intuition for convolutional neural networks, and if you're really adventurous, you can go and look at what's happening here in the second layer. This is now giving you a filter that's operating over not just this bottom set of activations, this bottom set of activations here, right? So you've got 2 filters, but it's concurrently doing it over this as well, okay? So it's processing over like the color image, right? You can think of these activation maps as almost like color channels. Of course, they're not colors, they're filtered channels. But nonetheless, you can now go and process multiple filters the same way that you might process multiple colors in an image. And it's the same analogy, and you can do this for 1 channel, you can do this for 3 channels, RGB colors, you can do this for 16 or 128 channels. It doesn't really matter how many you do, they're all just matrix multiplications. Then towards the end of the neural network, now you've got a whole bunch of these feature maps, right? And so we've made some more complicated features here, and we can look at where they activate. Great. We can downsample our feature activation by doing something called a max pool operation. This is really simple. All it is doing is it's saying over a 2x2 grid, just pick the maximum value. It's a way to decrease our resolution by a factor of 2 in the x direction and 2 in the y direction, right? So it's decreasing by a factor of 4, and this is done for computational efficiency, but it basically just gives us a coarse visualization of what's going on in this image. Hopefully it's giving you the same shapes. And then finally at the end of it, what you can do is something called a linear layer, basically actually just a complete matrix multiplication, or really inner product, where you are now taking all of those weights and you are doing an element-wise multiplication for each of them, and you're going to sum them all up and give you some sort of output. All right, So that output then needs to be calibrated to, you can have maybe one output, you can maybe have 10 outputs. Those can be calibrated to the 10 classes, which are the 10 handwritten digits. Or it could be, in your case, if you're trying to do a regression problem, a number that you are trying to force it to become something like your galaxy gas phase metallicity. So this is the essence of making training a neural network. It is even possible in Google Sheets or Microsoft Excel to make something actually train a neural network in it, but it's very painful, so I don't recommend you try to go that far in it. But this is good for developing your intuition. Actually, let me stop here and ask if there's any other questions. We've got about like 12 minutes left, which is all good. So this neural network, you don't want to, don't worry too much about this. It's very simple. This is actually the neural network, right? Like it is written in about 12 lines of code. I think. Does it use something up here? Okay, fine. I cheated. Okay, maybe in like 20 lines of code, right? And so what we have is we're going to define this convolution. In fact, we don't really have to define it too hard because it's already built into PyTorch. So we can just use it. And so what you have to specify is the number of input channels. So if you have a 3-band imaging with GR and I bands, then input channels equals 3. Then you have to specify how many output channels you want. That's basically how many learnable features you have or how many filters you have. So that can be any number. We can define how big our kernel size is. That's basically like how big is each of these little images. So if we say the kernel size is 3, it's a little 3x3 grid. The size of that little shape matrix. The stride is basically like, do we want to go and move one pixel over at a time? And I'm saying, no, let's go move 2 pixels over at a time. So we're going to skip over one at a time, right? And that's OK. This is, again, just being done for computational efficiency. We can then do something, I'm not going to talk about this much, but there's a learnable sort of normalization layer. You often need to continuously normalize your neural network because you're doing tons and tons of matrix products, and that can very quickly blow up to infinity or vanish to 0. And so by normalizing it, you try to keep it within a reasonable range. And then ReLU is just the very simple nonlinear activation function, which stays at 0 if it's negative, and then it's just y equals x if it's positive. Okay, so that's what this convolutional block is. It's just a shortcut of saying we're going to do 3 layers at a time. Each of these is done in sequence, so that's why we've wrapped it in this neural network.sequential, basically just a sequence of layers. And then we've gone ahead and defined a whole bunch of convolutions. So we go from 3 channels as our input to 32. So we're going to say we want to learn 32 morphological features. Each of them are 3x3 little matrices. After that, the next set of blocks will go from 32 to 64 features. And then we are going to go from 64 to 128 features in the third set of blocks. Now remember that we are doing a stride of 2, so we're skipping over every pixel at a time. So we're effectively downsampling our image. We're lowering the resolution a bit. So we're going from 160 by 160 images to 80 by 80 to 40 by 40 to 20 by 20. And so one of the tricks of machine learning that can be very challenging at first is that you have to keep track of like high dimensional tensors, and it's like very frustrating if you're not used to it. So very frequently you got to recall, oh yeah, what's in the 3rd dimension, what's in the 4th dimension, index. And this is probably the most challenging part or the easiest place to make errors by accident. So it just comes with time. If you keep doing machine learning, this is something that you basically just learn by practicing. We then downsample some more using something called an adaptive average pool. Pooling, again, is just downsampling. Average is exactly what you think it is. And so what we're saying here is we want to do averaging such that we result in a 5x5 set of output features. And so 20 is divisible, 5 is divisible by, or what am I saying? 20 is divisible by 5. So this will basically downsample by a factor of 4 in the x and y directions. And it gives us a 128 by 5 by 5 basically very coarse looking image of basically where it found all these features. And then we basically remove the idea of this 2D grid altogether, and we just say each of these, we're going to go and now make a linear layer. We're just going to learn coefficients, how important are each of these features at each of their positions, and then we're going to make a single prediction to give us the predicted metallicity. So this is this is basically what's happening here. We're defining all the layers, and then the forward pass is basically saying if you were to push our data set, our X, or our data, one at a time through the neural network, what would it do? It basically passes through the first set of convolutions, the second set of convolutional layers, the third set, and then what we wrapped in something called the head of the neural network. It's the last bit there. And then that will give us something that resembles a galaxy metallicity. Okay, so that's our architecture. Again, I know it's not trivial, but it's also only in about 25 lines of PyTorch, and it actually works. Okay, so that's about 100,000 parameters there. Let me, again, stop really quickly and see if there are any questions. Yep.
Can you please explain the downsampling part again?
Yeah. There's two ways to downsample. So one of them is if I take my filter and I say, okay, I want to know how similar is this filter? Sorry, you can see my cursor, right? Okay. So how similar is the cursor here, or the filter there, to the underlying input there? Now I could downsample by saying, I don't care what this value is. I only care about what that third value is over here, where I'm up here, right? So if I do that, then what I've done is I've skipped over one of those pixels, and I just said, I don't really care about the one in between. I assume it's something similar to the one to the left or to the right. So I'm effectively saying I'm just going to go and skip over some of these pixels. But because this filter is 3 by 3, it actually does touch the neighboring pixels. So it's actually acceptable, right? You are getting that information somewhere, but you're only, but you can choose not to. All right, I guess we're losing the projector. Another downsampling layer is if you do this max pooling or average pooling layer. And this is very simple. What we're doing is we're just saying pick the maximum value in this 2 by 2 grid of pixels. All right, I think this is going to be very hard actually to read. Can we get that back down? Do I use this thing to get that back down? Does anybody know? Oh. Is this the right thing to use? Yeah. Oh, it's over here. Okay, thanks. Okay, and so what we're doing is we're looking at a 2 by 2 grid and we're saying, what is the maximum value within that? So for instance, if I look at this one here, there's in this 2 by 2 grid, there's a 2, a 2, a 6, and a 7. So the maximum value is 7, which is why it gives you a 7 on that particular pixel. So you can do that. You can choose the maximum value. You can choose the average of the value. These are called pooling or aggregation layers, and you're just saying, how do I lower the resolution? But do I want to keep the maximum value, or do I want to keep the average value? You can think of these, if you have like a signal engineering background, as like the max pool is something like a high pass filter, and the mean pool or average pool is something like a low pass filter. All right. There is a lot of nice intuition that you can develop about how to optimize your neural network, but it's very challenging to think about this in 100,000 dimensions. We have 100,000 neural network parameters. They need to be jointly optimized, and so there's just no way you can intuitively say, oh, this is how we adjust weights in 100,000 dimensions, because they all covary with each other, right? All the weights work in tandem. And again, when I say weight, you should be thinking what is the value of this pixel in this filter, right? What does the shape look like? Well, that depends on the value of all the other shapes next to it too. So this is a very challenging problem if you think about it. It's hard to build up the intuition. But again, I think just by learning how to train these neural networks and just doing it in practice, you can develop better intuitions. One of the intuitions is, how do you update the neural network parameters? If you basically then have to decide how big of a step you take when you make an adjustment to the weights. So if you have some sort of error, you can then say by backpropagation, which I haven't explained, or you compute the derivative and you say, I want to take a very small step in that direction, which will improve that explains my error. Do I want to make a very, very large step, or do I want to do something in the middle? And what small and large are defined as are, again, just numbers that you have to sort of intuitively you figure out over time. But just to give you a sense of why you don't want it to be too low, if you have a small learning rate or you take small step sizes, then it takes you many, many, many iterations to train your neural network, because you're just making tiny incremental gains. You are defining your loss function here as a function of your parameters. And so your parameters basically if you change your parameter only a little bit, then it essentially hasn't changed. It's just as bad as it used to be. If you make too big of an adjustment to your parameter, what you want to do, again, is you want to minimize this function j, which is your loss function, right, the error. And so in order, the place we know, because we can see magically, how this error loss landscape looks, is that this is about the right place that theta should take on, theta being one of your neural network parameter weights. And so if we start out here and we take a gigantic step, well, then we go and say, the gradient points in this way. It says that we need to go this way in order to head towards the basin to the lowest loss, right? And so our linear approximation, our linear first order approximation of the gradient breaks down, and we take a gigantic step and we end up over here. And then when we go over here, well, then maybe we say, oh, we have to take another giant step because we're in some other part of the loss landscape. Again, we don't know where we are because typically you cannot see this whole curve. You only can draw samples out of it. You compute it and you say, oh goodness, my loss was no better there. And then you take another big giant step and you say, oh no, my loss is getting worse. And in fact, in this kind of scenario, you will diverge and you'll very quickly notice that your neural network would give you infinities or nans, which basically means that you need to start all over again. But if you pick a just right learning rate, then it won't take forever to get to the bottom of the loss landscape. It won't destroy your neural network and force you to restart, but you will get it just right. There are lots of other things I can talk about, again, and I have some references in here. There's even some math for the enterprising student. But really what you want to do is just be able to execute these cells. I think I'm basically out of time here, and I don't want to keep you guys too long. But what you can see is that when you train this neural network, you can evaluate what the loss looks like, what the root mean squared error is, as a function of training epoch. So each epoch is a full pass over the training data. And what you find is the training set is the data set that you are able to look at, your neural network has explicitly learned to optimize. But your validation data set is something that has never seen before. And in fact, when you try it in the beginning, it might be quite noisy. It's a smaller data set. And again, it's things that have never been seen before. But in just about, I think, 15 epochs, which is, I've done this on my MacBook. I can train this in like 5 minutes on my laptop. And you're able to train this neural network and achieve less than 0.1 dex error on the gas phase metallicity. Enough that, again, if you look at the CNN versus true metallicity, you end up with about a scatter of 0.093 dex. That result was the basis enough for me to essentially write a paper back in 2018. Now, of course, there were a lot of lessons learned and of how to get there and then implications of what you do with this information. But what I'm saying is that this is actually a very non-trivial, very powerful technique. Like this is something you can train on a MacBook. You can train for free on Google Colab. You can do it in like less than 10 minutes. And in fact, the power is in your hands. And you really need to think about what kinds of problems you want to solve once you are able to wield machine learning. I think it's fine to try all sorts of different things and see where it ends up failing. But ultimately, there are lots of interesting other problems out there that you can tackle. They don't need to use tons and tons of GPUs, but there are a lot of interesting physical problems out there, and I hope that you can put this information to good use. So again, I'm sorry I didn't get to go through all the neural network, the notebook. I think there's some bonus objectives down here if you're very interested. But these are the results. So thank you again for listening. Cool. Okay, yeah, I'm happy to take questions, but I think if people need to leave, feel free to leave too. Yep.
So I had a question regarding the augmentation stage. I think that you're rotating the image.
Yeah.
So like, did you use them in the training or validation, or like?
Yeah.
I don't know whether it functions like that.
That's right. So they have a particular inherent, like the image is on your disk or whatever, right? It's got it has a set, the image like that we load at the top here is got a particular orientation. What we've done is we randomly generate augmentations. So they're non-destructive or anything, but they are not preserved in the sense that like I don't think you don't know exactly like what has happened in a particular epoch that's already passed. This is something that you can set if you define a random seed. However, that's actually something that you don't want to do oftentimes in training, because if you set your random seed and you've never turned it off, then you effectively don't get the benefits of your data augmentation anymore. It can actually cause even more problems. And so, yeah, so that's a good point. Yep.
Visualizing it correctly, at every epoch you are rotating a different set of galaxies.
Mm-hmm.
And then, for for every epoch, it's like the galaxies are changing, and so in the end you are training and testing on the 14,000 galaxies themselves.
Yep.
But some of them are rotated over every epoch.
That's right. Yep. You're just coming up with a slightly altered view of them. They mostly give you the same information still, of course, right? Because if you rotate your image of the galaxy, I mean, it is true that it is different than before, but it contains, in essence, a lot of the same information. You can actually, it's a good experiment to try to see how different is your performance if you don't do any rotations and flips at all. And I think you do marginally worse, right? But it's not like a tremendous gain. It's just a helpful way, especially if you've run out of data. If you use all the data you have, you can actually augment it and get a little more. Yep.
So maybe two questions. The first question is, given a size of a galaxy, I was wondering how fast or how does the performance of the neural network deteriorate as the sampling of the image on that galaxy is reduced? In other words, from 100 pixels down to maybe 20 pixels. So that's the first one.
Yeah.
And then for the second part, leading after that, the kernel size in the demos of Q3, I mentioned that in the real case, it's not arbitrary. It sounds like arbitrary, but I don't think it's arbitrary. What tips for the size do we require?
Yeah, so the first question, actually, there's a lot of different answers because it's set by your hardware pretty, so it can be oftentimes, if you're using a GPU, it's set by the GPU bandwidth, right? It can be limited by file input and output operations. In my case, I actually changed this notebook and I made it something like an order of magnitude faster because I realized that, there's a little complexities, but basically on Jupyter, yeah.
I think I looked up these wrong terms, but performance in
Yeah.
sense of computation speed, I wasn't meaning that. I meant in terms of the performance in the recall success rate of the learning.
Yeah. How performant is your neural network? Yeah, that's a great question. Actually, so in the paper that I wrote here, we looked at that, so we can sort of downsample our images, until we literally just had like a 2x2 little thing. It gradually deteriorates. I'm not sure I can give you a particular answer except to say it just depends on your data set. And then for the second part, the kernel size, I mean, the traditional, almost always you'll find that people use like 3x3 filters, and it's because it often is more useful to have a giant library, like say 128 3x3 filters, than to have basically for the same cost of parameters, a bunch of 5x5 or 7x7 or larger filters, right? And you can think about that because that is scaling quadratically, which means that the number of filters in your bank for the same number of parameters that you want to incur is going to have to go down, also quadratically. And so it's generally more efficient to use 3x3s. Yeah. Some magical noises coming out here. Oh, that's yours. Okay, doesn't matter. I think we're probably good on questions, but I probably am running out of time slots to meet with folks. But again, you are always welcome to shoot me an email. My name is John Wu. I had my slides somewhere. Where's my slide deck? Okay, well, I've lost my slide. Oh, it's right here. So my slides, so my email is up here as well. So if you want to go and reach out to me, feel free to send me an email, jwuphysics@gmail.com, actually, or you can send it to me at jowu@stsci.edu. That's my professional email address. I'm actually not sure why I have this up here. Okay, all right, so thanks again for listening. Cheers.